All right. So let's see. So as far as acids and base goes, that kind of gives you some things that you should be able to do for this unit. I think probably the buffers, probably 3, 4, and 5. Well, that's over half of them. Are probably our hardest part. All right, so let's just start here, and we're just going to work through this review. We want to identify what type of solution is present because that becomes half of the battle. So looking through those different things, we'll kind of just identify them all. So NH3 is going to be a weak base. HClO4, that was one of our strong acids. Acetic acid, weak acid. NH4Cl, that would be a salt of a strong acid, because that comes from ammonia and hydrochloric acid. Number 5 would just be, I don't know, I just would probably classify it as a reaction. You're just taking a strong acid and combining it with a weak base. HNO2 in that one, that's going to have set up a buffer system, because my HNO2 would be my that would be my weak acid. My next one, number 7, that is going to be the salt of a strong base. Once again, my strong base would be sodium hydroxide on that one. Number 8, that would set up a buffer system. I would have a base, and then its conjugate would be supplied by that salt. Hydrofluoric, just a weak acid. And my last one would be just a mixture of strong acid. Oh, no, not strong acid, weak acid. Strong base. So that's kind of important that you can identify some of those as we work through them. Maybe it'll help a little bit. All right, so strong acid, strong base, those are the nice, easy ones. Memorize your strong acids, know your strong bases, because if you're lucky enough to get those are the ones that work through all these different formulas straight. pH is equal to log of your H plus concentration. I believe that one is on I believe these two are on your green sheet. Negative log, yes, sir. Negative log of my hydroxide concentration. And then also that the H plus concentration would be 10 to the raised up to my negative pH. That one is not on there, and sometimes that's handy. Negative POH, and then pH plus POH equals 14. So those are kind of all the things that we use mainly in AP chemistry, and they weren't so bad at that point. So to find the pH of a strong acid or base, you're just going to take the negative log of that acid or base. Remember, if you're working with the base, you're actually going to be getting your POH. Most of the time, the questions ask for the pH, so don't forget to do that little easy step that you will subtract it from 14 to go from POH to pH. And remember, when we talk about a strong acid or a strong base, that means that they are going to ionize in an aqueous solution. So that's what makes hydrochloric acid a strong acid. If I put that in water, I'm just leaving the water out, it's going to exist as ions. If I have hydrofluoric acid, bless you, we can write the ions, but this is a reversible reaction, and it's going to exist as the intact molecule a lot more. So that's the definition. Same thing with my base. If the more it ionizes, the stronger base it is considered to be. All right, so calculate the pH of a 0.45 molar hydrochloric acid. Remember we said if we have a strong acid, then it's just going to ionize. So if this is 4.0 molar, this is also 0.450 molar. So to get my pH, I'm just going to take my negative log of my 0.450. And that would give me a pH equal to 0.347, which is a low pH, probably expect for a strong acid. Remember, as far as sig figs goes, this is 3 sig figs. For pH and POH, the sig figs are what are behind your decimal. So whether I had this number or whether I had that number, those are both still considered to have 3 sig figs. Remember, it was the one that was a little bit different. And once again, there'll be an FRQ, or maybe we can go over it Saturday, that's all about sig figs. And then it's not that they don't look at sig figs, but they give you a little leeway. So like if it's supposed to have 3 and you did 2, they're going to give you, or 3 and you do 4, they give you a little leeway on those. Next one, I have a base is strong, so I'm gonna do the same thing. Negative log of my concentration, 0.710. Gives me 0.149, which is actually my POH. So I do 14 minus 0.149 is equal to 13.851. And somewhere on there, I need to, if I was actually taking it, I would need to make sure that I let them know that that's the pH. You know, and on some of these, it's on your FRQ, sometimes you do a lot of work to get to your problem. So it's probably a good idea to circle or box in or do something to your problem too, just to be sure. All right, weak acid or weak base, those are the ones that we have to use a rice table with. And I'll kind of set up one rice table to remind you, and then we'll do the other one where we kind of know what's going to happen. This is where we can neglect our X whenever we're going to assume that our X is small enough. If not, we'd have to use a quadratic, which are not usually on the AP test. All right, so you want to write a Bronsted-Lowry reaction showing how the weak acid or the weak base would be in water. So remember from that definition, a base is going to add a hydrogen ion, and an acid is going to lose a hydrogen ion. That's our good old definition. Put that in a rice table. Your beginning will be your initial concentration of your acid or your base, whichever one is your reactant. And this is where we're going to set up using our X for our concentrations of our products. Remember, once again, if you're working with the base, you're really finding your hydroxide concentration. So you'll have to do POH first and then come back to pH. All right, so we're going to do the pH of a 0.15 molar ammonia, which is a weak base. So if I put my ammonia and I mix it with some water, I'm going to get NH4 plus hydroxide. If we say it's a weak base, I got to have some hydroxides over there in my products. So this would be my R, and then my initial concentration, I just have 0.150 molar. Remember, we don't worry about the waters in here. And to start off, I didn't have any of these. And then my change, I'm going to, since this is a 1:1:1 mole ratio, if I lose X from my ammonia, then I'm going to have to gain X over here. So we end up at an equilibrium, 0.150 minus X, and then X, that doesn't matter that I have plus, and X over here. And of course I wrote too big, so I'm gonna have to write down into my other little one. All right, so we have our KB was given to us. So our KB, -5th, is going to be our products, which are our 2 x's. So x times x would give me x squared at the top. And at the bottom, I would have my reactant 0.150 minus x. And then this is where we're going to say x is negligible or something like that, which I'm sure I'm misspelling. So kind of do something where they know that it's not going to matter as far as what you would subtract from 0.150. That is an extremely small KB, but it is still pretty small where if I subtracted it, it wouldn't change that number that much because we deal with sig figs. Your math teachers would not agree with us because the numbers matter to them. So I'm going to kind of skip some steps for time's sake. So you got to bring this up and multiply and then take the square root. And when we do, we get 0.00164 molar. And you got to remember that that is equal to your hydroxide concentration. Get rid of some of my work. All right, so then at this point, Elliot, do not just all of a sudden get from that to your pH, even though you can do it all in the calculator. Okay? I have spies watching you that day, and I will come and bump your head. All right, so we're going to get, so my hydroxide concentration was, I already did that. So now to get my no, I don't want that. I want, sorry, y'all. Yes, I do. You don't have to on the multiple choice, but on the other part. So I'm going to get my POH first, which is going to be negative log. Like at this, I'm sure you'll say, oh, I can do that in the calculator. Not if you want those little points, you can't. All right, so I get 2.785. And then 14 minus that would finally give me my pH. A lot of work. All right, hopefully that's ringing a bell a little bit. Those still weren't too bad. I think the buffers are what probably are the hardest for all of us. Well, I should talk for other people. Hardest for me. All right, so now we have a hydrocyanic. So now I have a weak acid. I'm not going to do the whole rice table, but let's go ahead and do our equation. HCN plus H2O. So now if it's an acid, it has to donate that hydrogen. So that's how I end up with my H3O plus my CN minus. So if we set up a rice table, it's going to be that same pattern. So here I have my Ka. So I'm going to say Ka is 6.2 times 10 to the negative 10th. If we set it up, we don't know the concentration of that. So that's going to be x squared. And on the bottom, I'm going to have 0.227 minus x. I just skipped all that because we got the same pattern going on. And then we would work through, you would have to bring your 0.227 up and then take the square root of each. Once again, if I was really taking my AP test, I would probably make a little note right there. X is negligible in this problem or something. And so finally, when you get your X, it's going to be 1.186 times 10 to the negative 5th. And that one is my hydrogen concentration. So I can get my pH right away. So pH is going to go to the negative log of this little guy. You got to write him. You can't draw an arrow. And finally, I would get my pH, 4.926. Resid-fix. All right, any questions on that one? So for as many steps as you have to write out, those doesn't seem like the people grading it are that smart. I'm teasing. I guess they want to make, I don't know. I'm teasing. Just being sarcastic. All right, saltwater hydrolysis. Yay, I heard a yay. Not salt water, just a salt solution. Probably, no, never mind. All right, to find the pH of a salt solution, you first have to determine which ion within the salt will undergo hydrolysis. So remember your salt, you should be able to look at it and see which part came from a strong acid or base and which part came from which part came from a weak acid, weak base. You should be able to look at that because really the part that is the strong, it kind of doesn't become part of this problem. And the reason that is, if I'm talking about my ions that make up a strong acid, they're going to exist as ions. They're not going to come back to form a compound. All right, so you want to see which ion from the salt will react with water to form a compound that will not significantly dissociate. So that leaves any strong acids or strong bases out of the picture. So a quick way to figure that out is look at each ion and the salt and ask yourself, if this was paired with hydrogen or hydroxide, would I get a strong acid, strong base, or weak? We're interested in the weak for these reactions. So we want to find the one that makes a weak product so that it will not reionize. It won't break again into the ions, which would change your hydrogen hydroxide concentration. So once you've identified your weak, then you can write equation for the ion splitting that water, and that will become dr in your reaction line. Another important thing on this is that often you will be given a Ka, but when you look at the hydrolysis, you're using the conjugate base. So it's really a base reaction. So that's where you have to use that little 1 times 4, no, 1 times yes, 1 times no. I knew there's a 4 in there somewhere. 10 to the negative 14. That's your water is equal to Ka Kb. Because on quite a few of them, you'll have to get the Kb to actually use in your problem. All right, that is a necessary step for hydrolysis problems. Okay, so with all that fun stuff being said, I'm going to scooch this up just a little. So does anybody have any questions before we kind of get started on that? All right, I'm going to give myself a little bit more room. As I always manage. All right, so consider the pH of, I think that's potassium acetate. Oh, yeah, there's potassium lactate. So if I look at that and I break it up, that came from KOH. And then my acid part was HC3H3O2. This is a strong base, so I'm not really interested in that. I'm interested in this and the conjugate acid that it will form. That's what I'm interested in. So now when I look at these, I have to decide which one is going to hydrolyze or break water, and it's always going to be your conjugate. This isn't going to mess with water because it doesn't need anything else to be stable. This one, this conjugate really wants to be this guy. Yes, ma'am. From this right here, oh, did I write it wrong? It's supposed to be a 5. I'm sorry, Elizabeth. Thank you. I feel like and that just something else. It's supposed to, I'm sorry, it's supposed to be that part. Sorry about that. I feel like I was also doing that in regular chemistry today. So you have to get the part that is either the anion if it's an acid or the cation if it's a base, and that becomes your reactant. Let's see if I can write it. C3H5O3. If I add it with water, it's going to grab one of those. What have I got going on here? This is going to grab one of my waters. Not one of my waters, one of my hydrogens, and I will have, what am I saying to myself? This, I feel like I'm saying the wrong thing. This hydrogen is going to come over here. I'm going to be left with my hydroxide plus my weak acid. Because remember, that acid, it's not like hydrochloric acid. It doesn't want to be in ions. It wants to be together. So what you need to realize at this point, we may have started out with a weak acid, but when we wrote this hydrolysis equation, this is actually now a base equation. Because that conjugate base brought on a water or took on the water. So this is a base equation. Yes, ma'am. On this part right here, no. On this part? Because you're looking for something that when it reacts with water will stay together. This potassium, it comes from potassium hydroxide. And those, no matter what I'm going to do, are going to stay as ions because they're more attracted to the water, which would surround these, than they are attracted to each other. So that's why when you look at your salt, you need to figure out which half of it comes from something strong. And then you kind of just ignore it. Because what you're really interested in is the part that is going to come from a weak acid or a weak base. So now, so originally we were given the K, we were given the Ka for this acid, but we didn't use that acid. We used its conjugate base. If I just wrote this out and pretend like I'm not going to get the numbers wrong there. If I wrote this reaction, this would be my acid and it would donate. That's an acidic reaction. I end up with some hydroniums, but we weren't interested in that. That doesn't help us in this. We're always interested in the conjugate on these. So when I flip it, it's going to end up becoming a base reaction because now this doesn't donate a hydrogen, it accepts the hydrogen. See the whole point on these, I mean, and I agree they're hard. The whole point of these, we're trying to find that because that salt's going to stay together. That's what allows me to set up a buffer system. I have something that the hydrogen, if I put in a strong acid that it could react with, if I put in a hydrogen, it could react with that part and go to that. If I put in a base, it could grab that hydrogen and form water. So either way, it's not going to increase the H plus concentration or the OH concentration. So it's not going to change the pH. That's why it's a buffer. Because there's something, if I put in something strong, there's something that it can react with. Does that help some? Okay. All righty. So let's see. So my first thing I'm going to do is I know I'm going to need my KB. So I'm going to go ahead and do that. So my KB is going to be equal to 1 times 10 to the negative 14, which if you forget, like I seem to be forgetting today, it is on your green sheet. So that's going to give me my KB, which is 1.4 times 10 to the negative third. So if I write my reaction for this, I'm going to have, let's see my next little. So I'm going to have my, what did I do here? What am I at on this one? So I'm going to have my KB is going to be equal to my hydroxide concentration times my acid concentration divided by this ions concentration. I just set it up is all I did on that one. And this should have a charge on it. So now I'm going to start filling stuff in. I figured out my KB. I don't know. These are the two things I don't know. I don't know this and I don't know that. So those are both going to be X's. So that's where I'm going to get my X squared. And I kind of just shortened it a little bit. You could put this all in a rice table. I do know this concentration because this concentration came from that. Because remember, potassium is always going to be soluble. So that's going to ionize. So I'm going to say 0.95 minus X, which we're going to end up, once again, not worrying about. All righty. So when I do all that and I solve for my X, I get that my X is going to be equal to something. I think this is it. 0.036 molar. Is that what you got? All right. These are, no wonder I can't figure out why I'm getting lost. All right. So, but you got to remember this one is your hydroxide concentration again. So once again, you got to go through all that. I'm going to take the negative log. And when I do that, that's going to give me actually my POH, which is 1.44. And then 14 minus 1.44 is going to give me 12.56, which is going to be equal to my pH. Woo! A lot. That's a lot. That's a lot. All right, questions? Joseph, you got a question for me? Lizbeth? Yes, no? All right. So I think our next thing we go to is a buffer solution. Got myself some working paper there. Now this one shows using the Henderson-Hasselbalch, or however you say it, equation, and actually then it does put the equation we've been using down a little bit farther. Did anybody work into these problems using the whatever the HH equation? No? Okay, so I think we'll stick with ours. So in a buffer solution, it's always going to contain a weak acid in its conjugate base or a weak base in its conjugate acid. It's not strong. That's not going to form a buffer system. I did on here. Look, this one said Glenn. That means that was my third type I did. The problem is that, well, you'll see here in a minute. The problem is that your acid-base equation was equal to 1. So my question is, did it only work out because of that? So I need to find one that has not, we're not necessarily at the equivalence or half endpoint. Okay. His brain probably would like a break. I told him I can't figure out why I keep getting lost in my notes.
I couldn't see 1 hour.
And I just looked over these two. You're welcome. All right, let me see if I can figure out what's going on here. So I did our technique. That's my note to myself. All right. So I'm going to move this up here some. Maybe. All right, let's see what we got going on here. All right, so calculate the pH of a solution, which is 0.53 molar, whatever that is. Is that the same thing as we used a minute ago? I don't know. I don't feel like it is. That is my weak acid. It starts with hydrogen. That's my weak acid. This is my salt. I am not interested in the sodium from that salt. That sodium came from, it would be, yeah, sodium hydroxide. That would be considered a basic salt. I'm interested in this C6H4NO2 minus, which is the conjugate of my weak acid. All right, so that is what I'm interested in. So this is going to be what is going to hydrolyze or break up the water. Whichever one has the charge, that's going to be the one that's going to break up the water, and that should end up becoming your reactant. So for an acid, that's going to be the anion or the negative ion. So this C6H4NO2 minus, if I put that in water, then I'm going to end up getting back my weak acid and some hydroxide. Is that actually what I'm interested in here? That may not. Yeah, let's see. Hold on 1 minute, y'all. I think I know. I'm sorry. I got myself confused between my salts and this one. I'm sorry. So on this one, and once again, I'm not going to lie to y'all. I find these hard myself. I am interested in what is going on here, because if I do this one, I can go straight to my hydrogen ion concentration. So I'm going to combine it with some water, and we're going to get my H3O plus, which is the same thing as my H plus, and then this H4NO2 minus. All righty. And that is an acidic reaction, and I do have my Ka. So then we can use our formula that we've been using, which is this formula right here. So I'm going to say my H plus is going to be equal to my Ka, which is 1.7 times 10 to the negative fifth. And then my acid is going to be this concentration. So that is 0.53. And my base here is my conjugate base. So that is my 0.50. And then I think you can put all of that into your calculator. And I end up getting an H plus concentration, which is equal to 1.80 times 10 to the negative fifth. So negative log of that is going to give me a pH equal to 4.74. 2 sig figs. So the difference between the last one and this one, I started trying to do this like a salt problem, but this is a buffer problem. If you just go back and glance at the one before, it didn't tell you you had a couple of things, you just had a salt. So that is the one that we had to work a little bit different on that one. All right, next one. Y'all want me to work all the way through this one? This is now, instead of a weak acid, I got a weak base. Yes, no, just a nod of the head. Yes. Okay. So I'll leave this to y'all if you want to, and then we can always check it on. Saturday. This one, when you're all said and done, you should end up with a pH of 9.255. That is your weak base, and you're interested in the NH4 part of that. Now, this one may have been, I think this is the part, I'm just going to skip a little bit. This one, let me get my little note to myself. Which one did I do? 7A, Glenn, not Glenn. All right, this one. So on this one, I'm just going to set it up. So this one, we would have said my H plus concentration, and I'm jumping ahead, is going to be equal to my Ka, which I would have had to figure out, times 10 to the negative 10. And then I would have had 0.245 over 0.245. So that ends up being 1. So this means you're at your half equivalence point, because your H plus is equal to your Ka, or your pH is equal to your pKa. So this one actually could have been done several ways if you realize that you were at that point ahead of time. So this is what I was talking about, Elliot. So like, this is the one that I happened to try using Glenn's way, where we just stayed with our KB. But since this is one, I didn't know if it just happened to work in that one I chose to try, or if it would work every time. So I feel like I need to try one where that would be different. Mhm. No, you don't have to do it in that. If we're going to use this formula, you are going to have to, because that's going to be your Ka. You're going to figure your Ka. But if you go back up to that Henderson-Hasselbalch, like you have this one that you could use, and you wouldn't have to switch. You wouldn't have to worry about, if it was a base, you wouldn't have to worry about going and finding your. So if you want to, Michael, maybe try some of the, maybe, and then we can talk about it again on Saturday. And then this is always your ion over your base. And it says, if you're going to use that one, remember I am on top. So the ion is on the top. All right, where are we at to now? Method 2, I think we already did method 2. Method 1 here was the Henderson-Hasselbalch. All right, let's see what we're doing here. All right, so if your buffer system, start by identifying the component that is easy to recognize as a weak acid or weak base. And that concentration is the one that will go in your brackets for your acid or for your base. And the conjugate, like I said, we kind of just tend to not call them conjugates anymore. The conjugate of that weak acid or base is what will go in your remaining bracket. So this is talking about the formula that we've really been using most of the time. And once again, if they give you a KB, you have to do that little Ka conversion to get there, because that is part of the formula that we've been using. You might want to try the Henderson-Hasselbalch and see if it works better for you, and we can touch again on that Saturday. All right, so calculate the pH of a solution. Once again, I got some kind of acid. I have some kind of salt. I can see sodium is strong, so I'm interested in this part. So this is not just a hydrolysis reaction like the one on the other page. So my reaction for this is going to be my HC6H4NO2. That's my acid. Joins with water to give me H3O plus. And that's an acid. So this is my conjugate base, C6H4NO2 minus. And that is an acid reaction. So we just can plug in all of our information. We're going to use our formula we've been using, which is just right above this problem. So I'm going to say my H plus concentration is going to be equal to my Ka. So that's going to be my 1.7 times 10 to the negative 5th. And then I'm going to put my acid, which is what I started with, my 0.53. And that goes over my base. It's in alphabetical order. Acid on top of base. This is my base. It doesn't look like a base that we did with Chem 1, but that's because it's a conjugate base. And then we'll do all of that And we would end up getting a pH, when all is said and done, of 4.74. Next Monday, you wouldn't skip right to that. You would show a little work to get there. So questions on that? I feel like, and Michael, I've tried really hard to find some indicator problems, and they are really hard to find. So I'm still working on that. I feel like here that maybe if I found another salt hydrolysis reaction, like the one we did on the bottom of that page right before it, that may be helpful. I feel like that may be kind of a weak area. All right, where are we at? Got time for a little bit. Got one more yellow note left here. I have no idea what it is. All right, let's see what we got going on over here. All right, so this one now I've got a weak base. See, this one ends up being, it also ends up being at the half equivalence point, so I couldn't check lens this way either. This is my weak base, and then here I'm interested in my NH4 because my chloride would come from my hydrochloric acid. So if I wrote my equation, I would have my NH3 plus my H2O is going to give me my NH4 plus. And remember that when I need it as a buffer is coming from the salt plus my OH minus. All right, and it says we said it's a base, we got to have some hydroxides whenever we make that. So once again, we're going to go through the similar situation. I think I did on this one, I did use the Henderson-Hasselbalch since I had KB. So I'm going to just jot down that formula. You may or may not choose to jot it down. KB plus log of your ion, in this case over your base. So that way I didn't have to change my KB to Ka. So I did POH is equal to 1.8 times 10 to the negative fifth plus the log of my ion is from my salt. So it would be my 0.245. And then that would be over, oh, they both are. So once again, I'm at that. Remember when the concentration of your acid is equal to the concentration of its conjugate, you're at the half equivalence point. So you could have just done, if we would have realized that, my pH would be equal to my negative Ka. So once again, it was that 1-to-1 ratio. So you can really check. All righty, I am going to record those last two tonight, even if I have to stay here forever, because I feel like we got to move on. Y'all remind me tomorrow to get taco orders. All right. Y'all have a good rest of your day. Thank you. Stop recording.